This is the review for Chapter 17, Additional Aspects of Aqueous Equilibria. So Section 1, we have the common ion effect. The common ion effect is based off of Le Chatelier's principle. And Le Chatelier's principle is saying that whenever something is done to a reaction, the reaction always acts to lessen the stress of whatever that change is. So if you remember, you'll have some sort of reaction. So you'll have A plus B yields C plus D. So if I add more of D, then it's going to want to get rid of that extra D that I added in here. So what it's going to do is it's going to make more of A and B by increasing the rate of the reverse reaction. And if that rate of the reverse reaction is going to increase, then C is going to be used up more A and B is going to be created, and then D is going to go back to the original. So A concentration will go up, B concentration will go up, C concentration will go down, D concentration will stay about the same. So just remember that when we're talking about the common ion effect, what it is it's looking to relieve the stress on the system. So if you add something, the system will speed up either the forward reaction or the reverse reaction in order to make sure that whatever you added to the reaction will decrease. And if you took something out, it will increase by changing the rates of those reactions. So let's start from the beginning here. Notice that these solutions contain two substances called a common ion. So we talked about before in chapter 16 how something like acetic acid will dissociate into let's see here, we got H plus, I believe this is this dissociation. So it'll dissociate into those ions. And then we have a salt here, CHCOONA, so sodium acetate. And what do we know about salts? We know that they'll dissociate into different ions. So that salt's going to dissociate into the Na and the CH3COO minus. So what do you notice about those two? Well, we have the weak acid, which is acetic acid, which dissociates into that. We have the salt, which dissociates into that. They both have what's called the common ion, which means they're going to dissociate into the same thing. So what happens when you add the salt into the solution? The concentration of that common ion is going to increase. So we look here, you have the dissociation for the salt that I just had here, the dissociation for the weak acid, acetic acid. You have that common ion because they both dissociate into the same thing. That's the key here. When you have two things that dissociate into the same thing, they have a common ion. So if you're adding the salt to a solution, you're increasing the concentration of this common ion because, or sorry, this is the salt up here, because when you add the salt, or you could even add the acid to a salt solution, you're gonna have more of that common ion. So just like I talked about before with Le Chatelier's principle, when you're adding the concentration of something on the reaction, it's gonna shift in order to lower the stress on the reaction. So if we're adding to the concentration of CH3COO minus here, draw here. So if we're increasing the concentration of this, the system wants to decrease the concentration of this, right? So like we're increasing the concentration, we want to decrease it to get it back to the same level as it was before. So how do we do that? We increase the rate of the reverse reaction, meaning that we're going to use up these faster and we're going to form more of this. So this concentration will go up and then this concentration will go down because remember, we're using this side faster now. So the main effect is that the reverse reaction for something like this is that the hydrogen concentration, the H plus, will decrease and the concentration of the original acetic acid will increase. That's basically the common ion effect. If you know Le Chatelier's principle, biggest thing to know is that it's looking to relieve the stress in the system So you're increasing the concentration of an ion, it's going to shift, and the rate of, in this case, the reverse reaction will speed up in order to use more of the ion that you have in common. Whenever a weak electrolyte and strong electrolyte containing common ion are together in solution, the weak electrolyte ionizes less than they would be if they were alone. Okay, so this is the fancy way of saying what I just said, where since it's shifting to make more of the reactant, since more CH3COO minus is going to be made, it's going to dissociate less because more of it's staying in the form of CH3COOH than it is breaking up into the ions. Sounds confusing, but just remember, if you're adding more, or if you have a common ion, you have more of that ion in the solution, you want to shift away from the side that has that ion on it. So the reaction is going to increase in rate in the direction away from where that ion is. Buffers. So what a buffer is it's a solution that contains the high concentration of a weak conjugate acid-base pair. So this comes in two forms. We can have something like, I'll give you an example, HF. It's a common weak acid. HF is a weak acid, so what will be the conjugate base of HF? Well, the conjugate base is HF after it loses the hydrogen. So the conjugate base would be F minus. So this is the acid. This is the base. So if we have HF and F minus in a solution, those would be an example of a buffer. Another way that this is commonly written is HF and then something like NaF. I don't know if this would actually form. This is just an example. So HF is still the same acid that we had before, but now NaF is a salt. And why did I choose NaF? Because if you remember from the rules of the salt, since the Na came from NaOH, this will have negligible acidity or basicity, so it's not going to affect it at all. And then since the F came from a weak acid, it's going to turn the salt, it's going to change the pH of the solution by making it more basic. Because remember, the conjugate base of a weak acid is a weak base. So if you see it in the salt form, or if you see it like that, it means the same thing. That's an important thing to remember. So don't get tripped up. Commonly, you'll see it like a weak acid and it's an salt with its conjugate base in it. That's what that means when it says that. A weak acid and a salt with its conjugate base. So a good example of a buffered solution is blood, yada, yada, yada. Buffers find many important applications. Basically what a buffer is it makes the change. If you add an acid or a base to the buffered solution, the change would be less in the pH than it would be if you didn't have that buffered solution. So moving on, buffer resists changes to pH because it contains both an acid to neutralize and added hydroxide ions and a base to neutralize H+ ions. So why does the buffer work? Because remember, we have the HF and the F minus. These are just examples. So let's say we add a base here. Let's say we add NaOH, which is a strong base. What's going to happen? This acid plus the base will combine and you'll form water and a salt. And then this will not affect it because this is considered a neutralization reaction, and it talks about this down here. Neutralization reaction is something that forms water and a salt, and it's the result of mixing an acid and a base. So if you have the acid here, the conjugate acid, if you add a base, the conjugate acid can help neutralize the base. Likewise, if you add an acid, so let's say I add HCl. which is a good example of a strong acid, it will go with the weak conjugate base and it will get neutralized and form HF and Cl minus, which again will not affect the pH as much. So know that if an acid gets added, the weak conjugate base will cancel it out, and if a base is added, then the weak conjugate acid will cancel it out. That's how it works, is that since you have that conjugate acid and base, they can both be used to neutralize a strong acid or a strong base if it's added. So this is talking about how it works. Common equilibrium reaction for a weak acid. Some algebra here, rewriting the equations. So this is just going in detail to what I said, where if you're adding a acid or a base, it's going to get neutralized by the conjugate acid base pair. Again, that's a complicated way of explaining what I just talked about. Calculating the pH of a buffer. So this is a good equation to know. We're going to get down here and we're going to find that this is I believe it's the Hasselbalch equation, I think it's called. You don't need to know that. What it's saying is that the pH plus pKa equals the log of the base. So I'll give you an example. Let's say we have HF. You know what? I'm not going to do an example of this. This is just straight plugging in. This is on your reference table, and you're going to take the concentration of the base after over the concentration of the acid. So you'll see here they have A minus for the base and HA for the acid. A minus would go into here, your concentration. HA would go into here, your concentration. So then you get you can find pH, or you can even rearrange it. If you want to look for POH, it could be substituted with the POH plus pKb plus the log of the acid over the base. You kind of just swap it around for a base. I'm not sure if they show that here. Just read this over. Yeah, here it is, the Henderson-Hasselbalch equation. Again, this is on your reference table. You're really just plugging in here. You'll know when to use this because share a common ion will use. Let's see if they can go down here. Let's see if they have another example for that. So these are just more examples of you're basically just plugging into the Henderson-Hasselbalch equation. You see you got the pH, they calculated the Ka up here to be, what did they do it, 1.7 times 10 to the negative fourth. If you take the negative log of that, remember, because P means negative log, so you take the negative log of that, equals 3.77. You just plug that into your equation, and then the 0.1 over the 0.12 would come from, let's see, in the question they gave the concentration. Where did they give the concentration? Concentrations here. So you're taking the concentration of your original acid, your weak conjugate acid from your buffer, and the concentration of your weak conjugate base from the buffer, and that's what you're using. You're plugging into that. Really, it's just plugging in. I'm not going to do an example here because they did the example here for you. pH, you find the Ka, take the negative log of that to find pKa, plug that in, then you do the log of the concentration of the base over the concentration of the acid, right? Concentration of the base over concentration of the acid. That's on your reference table. You're just plugging into that when you need to. Buffer capacity and pH range. All this is saying is that a buffer only works for so long. Think about it. If you add enough of a strong acid or strong base, yes, eventually it will change the pH of the substance. But the point of a buffer is that it takes more of that to severely change the pH. So good buffers can keep it within +1 or -1 of the pH. So let's say the original solution has a pH of 4. if I add a relative amount of strong acid or base, the most it'll go up or down is to a 3 or a 5. It'll stay in that range. But again, if you add enough of it, it's going to change it, but that's not really important for calculations wise. Addition of a strong acid or bases to buffers. This is because this is what I was talking about. The neutralization reaction between strong acids and weak bases proceeds essentially to completion as those of strong bases and weak acids. So remember I said that if you add a strong acid, it's going to be neutralized by the weak conjugate base. And if you add a strong base, it's going to be neutralized by the weak conjugate acid. That's how the buffers work. That's why the pH doesn't severely change, because remember, in a neutralization reaction, you're creating a salt and water.